let's go here. Okay, great. Chapter 11, guys, talk about HVAC equipment. For HVAC equipment, I chose a couple of things to just get you into the mood of the HVAC equipment. Could you please grab that colored piece of paper that I have in front of you? Colored piece of paper. This has been shared with us from our mechanical department here. I'm just going to let you guys look at a couple of things in a second here. So, HVAC equipment. For us guys, HVAC equipment, it's heating and cooling the building, basically. How are you going to heat and cool the building? There's a few things you have to keep in mind when you go to heating and cooling commercial buildings. Heating and cooling commercial buildings. So, if you guys don't mind, just go to chapter 12 with me, guys. Ventilation, air conditioning of the facility. Let me see if let's grab. So if you guys go there while I energize my stuff here. And okay, so before we get into the terminology, so that's good here. This one, guys, I picked this one because this is typically a high profile cooling system for a commercial building. Really high profile cooling system for a commercial building. I want you guys to look at a couple of things to identify. I want you first. There are two of them. They're chilled water piping schematics, and the second one is condenser water piping schematics. The way this system is work, these are huge mechanical equipment. Oh, come on. Tell me that you're going to allow me to draw these. Brad, did you screw it up, buddy? Oh, every day. I hate it when it doesn't allow me to draw things. Okay. Let me see if I can get it here. Highlighter. All right, now can we? Okay, good. Okay, I want you, before I go ahead, guys, I want you to look at these two systems. These are, I can't try to see if I can fit it in one page. You guys are looking at the two together. This is actually one complete system. Just, you don't need to understand how it works, but it really makes your life much easier if you do. You know what they do? I don't. Did I give you one? I give each one of you guys get one. No? So you should have one of these, guys. The way they do it, and it's colored. The one that you guys have is definitely colored. So if you look at this, what they do, guys, is they take the this is the chilled water. I want you to look at two things. Can you guys see where the chillers are? Where your chillers are located? Here's my chillers here. How many chillers do I have in the system? I have 1, 2, 3, 4, 5 chillers in parallel. 5 chillers in parallel to chill the whole building. Huge building to have 5 chillers. And if you guys were with me when we went to Boston Scientific, did you see how big these chillers are? They can fill the whole room. Huge chillers, almost as big as a generator. We have 5 chillers. They're chilling. The job of the chiller, Brad, is to take to basically there's a compressor on them, and they compress refrigerant, and they create cold. They get the heat out of that refrigerant to create the cool. So what they do, guys, a couple of things very interesting to see, and I don't claim to be an expert in that. What they do is, let me look at that one. They circulate. I'm gonna just use the blue here for mine. The blue is the cold water. Can you guys see that cold water is coming? Cold water. When it's coming, it will be coming. Let me see here if I can grab my highlighter. Okay, now we're talking. So if you guys look at the cold water at the top, coming out of all this is all cold water line and going to, these are all in parallel. And believe it or not, each one of these guys, air handling unit -1, air handling unit -2. Does that now make sense to you guys? air handling unit -3, air handling unit -4, and air handling unit. No, this is not an air handling unit. These are just air handling units. We have 4 air handling units receiving chilled water from 5 chillers. Then you can see the blue is the chilled water coming from 5 chillers. So here's what they do, Spencer. They chill the water, and then they have pumps. Can you guys see that pumps? The pump that circulate the chilled water all the way to the air handling unit. And everybody knows what the air handling units are as. Air handling unit is just these coils. It looks exactly like a coil, and then big blower and blows the air through these coils. Now these coils are full of chilled water, cold. So what happens if you guys blow an air through pipes or coils that's full of cold water? You blow the air from this side, from the other side you get what? Chilled air. That's the cool air that you get and you circulate in your building. Very easy. So what they do, the compressor, through the compressor of the chiller, guys, they chill the water, and then they circulate the water into the air handling unit. And inside the air handling unit, they have big motors, fans that blow the air through that chilled water, and they get you the cold air. So one more time, the chiller is to chill the water. You have the chiller to chill the water. Then you have to have pumps. Can you guys see the pumps here? The pumps will circulate when the water is. Now after you get it, see how they parallel it back? This is hot water going back to where? To be chilled again. Can you guys see how easy that? It's exactly like we parallel. And you really don't, as I said, don't need to know all this, but it really makes your life much easier. So after the water has been chilled, after you blow the air out of these coils, the water inside the coils become hot. So they take it back. Look at that. How do they take it back? Through pumps. They pull it back and they take it back again into the chiller, and they chill the water again and keep rotating the chilled water into the air handling units. And it's a closed cycle loop, guys. They keep bringing the water into the chiller, chill the water, take it to the air handling unit, blow the air through it. Now we've got cold air. The water got hot now because we blew the air through it. Take it back to the chiller, chill it again, and keep circulating all these systems together. Now, you can, depending on, and there's a lot of control involved in it, depending on how much chilled water you need, you can accelerate the fans here with VFD, guys, to get you more or to control the heat, the cool, or you can control the pump, the chilled water, how much chilled water can get into these air handling units, or you can shut down certain. You don't need all these 5 if you don't need all this this chilled water, depending on how many chilled water you need. These are like parallel generator, Brad. If you have 5 parallel generator and the load went down and now you need 3, what do you do with the others? Shut them down safely through the control system. They shut down these chillers. Some of them are redundancy. It will sit there just in case one will fail, the other one will take over. So there's a lot of redundancy in the system. But what I want you guys to understand is, it's a closed loop. They have water, and they circulate the water from between the chiller and the air handling unit coils. The chiller will chill the water. The air handling unit will actually heat the water because they blow the air through it. The water becomes hot, and they take it back to the chiller again. Any question, guys, about this, Camille? Now, for us, electrically, what do we care about? Electrically, that's the mechanical, guys. Electrically, what do we care about? Brad, here's what you need to do. Air handling unit, you need to power this one. Number 1. We know how to power an air handling unit, right? It's a horsepower. All what you have electrically in the air handling unit, guys, is a big blower, 1 or 2 blowers. Sometimes they have in and out blowers. So it's a blower. What does a blower need? It needs a control, VFD, and it needs a motor. You guys have done it for me. The project that we have has 3 air handling units, in and out, left or right, if you guys remember, and you powered it. That's all what we interface electrically. The second thing, Brad, is see these pumps? What are these circulating pumps? These circulating pumps, number 2, all these need power. So we need to power them. They're pumps. They need power and control. So either you give a VFD for them to control them, or you can control them with an EMA, but you still need to power them. And the last thing is the compressor, guys. Look at these. Each one of these need a power. This is number 3. Do you agree with me, Spencer, that these are the chillers like you guys have on our project? What do they need? They need power. They have in tons, so you need to power them. Electrically, that's how we interface with the mechanical guys. Can you see from the air handling unit into the chiller, into the pump that circulate the water? We need to power them. We're not responsible how the system mechanically work. I mean, the mechanical contractors and engineers will take care of that. We power them. This is where you get, Brad, all your mechanical equipment schedule. They're pulling it directly from these systems. Any question, guys, about this? Any question about closed loop? This is, they call it the chilled water piping schematics, closed loop. Closed loop water going from the chiller to the air handling unit and back. Chiller, air handling unit, back. Chiller, air handling unit, pump back. And they keep circulating that water. And I'm simplifying it, guys. There's a lot of control and a lot of valves to make the water goes in one way, not the other. Any question, guys, about the top one? Now the question becomes is, what the heck is the bottom one, Chad? What the heck is the bottom one? Okay, so everybody understand the top one? The top one? Now, believe it or not, and that's the confusing for a lot of people. Do you remember that water that's coming? Do you see that hot water that's coming in here, guys? That hot water. Do you see that hot water that coming in here? When to cool the hot water before they compress it again, before they chill it, to cool it down enough before they chill it, because it's hot, it gets hot. To cool it down before they chill it in the chillers. Okay, before they chill it in the chillers, they have to cool it to a certain level. You know what they do? They actually put it in have another water cycle that cools it. So look at this again, guys. This might be the confusing part of it. So here you go. You come up, cooling towers. If you guys look at the cooling towers, these cooling towers are grabbing hot water. Cooling towers. All these cooling towers are grabbing the hot water in here, and they're coming. Did they bring it down to I'm just going to say down to the chiller, and they have another cycle, and that's coming out of here with another bunch of pumps. Bam, 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 and they're coming over here. Without confusing you guys too much, they have two loops. One loop is the one that goes to the air handling unit. That's the one that we love. The second cooling loop is to chill the water that's going to the air handling unit. So what they do is that, see that water in here, the water that's in here, they have another loop, guys, that they chill the water. There's two loops of water. That's what the confusing part. Two loops of water. One loop goes to the air handling unit. That's what we love. The other loop chill the loop that goes to the air handling unit. Okay? So that water here somehow gets into a location, guys, inside the chiller, where we chill it by water first before we chill it again with a compressor. We chill it by water. So we put water around it, guys. And here's what do you guys expect these pumps to do? These are pumps basically pulling the water between the cooling tower. Now, what is the cooling tower? You're going to hear people talk about cooling tower, guys. See that when this has become so hot, they bring it to the chiller and they put water around it. These coils go through water, and the water gets hot. So they take that water all the way up to the roof of the building into a chiller. And if you, when we will be going, guys, on Thursday to Allianz over here. They take us to the roof, and please look at their chillers. Their chillers, it's a big, huge tower sitting there, and at the bottom, it coils all over, full of water, and all what they do, guys, and big blowers at the bottom of it, and they blow air through these coils to cool them down, because they have hot water now coming from the building. So, electrically, what do we interface, Brad, here? I need the cooling tower, here's number 4, that need power because it has fans. This, and this. Each one of them need a power. And you're talking, Brooks, about 50 horsepower, 3 or 4 in each one of these cooling towers. It's not unheard of, guys, to have 2 fans, 50 horsepower each, for each one of these cooling tower. And all what they do is they're big blowers, blow air right through coils that's carrying hot water. And when you blow air outside the building through a hot water, you're getting the heat into the out. You're basically cooling the water, right? You're getting the heat out of these hot water into the environment. Then by the time, then you get it, then it cools down. And you can see how they cool it down again. Right here, it cools down and goes back to these tanks. that take it back again to the chiller. This is very similar to the air conditioning that we have, guys. Our air conditioning, we have the condenser and the evaporator inside and outside, and it works together. This will be equivalent to the condenser outside, and this is evaporators getting the heat out of the system. The heat out of the system. What do we care? We care that there's blowers here that need to be powered, number one. And so here's 4 things. The last thing, what do you guys expect these pumps to need? These are different pumps. See these pumps? 1, 2, 3, 4. Oops, I should have used the green. 1, 2, 3, 4. Oops, I have 5 pumps that need power. That's my interface with the mechanical contractors. I need to provide power for the air handling units. Power. By the way, these chillers are the same chiller. By the way, these are the same chillers, but they're showing different systems. The air handling units, the chillers, the pumps that circulate the chilled water, also the condenser water pipe. The condenser water pipe, they need pumps here, condenser pumps. You need to power them, as well as the cooling tower. There are two water loops. One water loop, chilled water, guys, go to the air handling unit. That's what we love. The second water loop is the condenser water piping schematics, guys, and that water actually chilled the water that goes to the air handling unit, if that makes sense. So 5 major things, and there's other valves. Sometimes you have a valve here that need to be powered, but these 5 major things in any major building, and this is, guys, as high as you can get. This is a really complicated system. This is high-end system when you have 5 chillers in parallel with 5 cooling towers in parallel with each other to carry the heat, the cool. This is just cooling the whole building. Any questions, guys, about this? What I like, I hope you keep this one, guys, really good. Egan, you guys work at Egan, they have tons of these. I mean, if you talk to the mechanical engineers, they'll be able to walk you step by step through how this system works. This is just a crash course in heat and cooling system for commercial buildings. What I did, guys, when I start working in the construction industry as an engineer, the first thing I went, because it confuses the crap out of me, what is the cooling tower? What is the chiller? I sat with the mechanical engineers with a sheet like this and said, explain how the system works. I know how to power it, no problem. I can bring power to all these, but how does it work? So, and what I told you guys is probably 50% of what the system is. If you need more information, when you work in the field, just talk to the mechanical engineers. But for the most part, there are 2 chilled water loop. One goes to the air handling unit, the other one chilled, the one that goes to the air handling unit. Any question, my friend? Any questions? Now, they don't have it here. The question, guys, well, how do they heat the building? How do you guys heat the building? This is just to cool the building. To heat the building, guys, they have another coil like this right here. It's not an arm. They have another coils like this, and they bring hot water. There's a boiler with pump, and this is just simplifying it, guys. And then look at that. And they use natural gas for the most part. Brooks, my friend, a lot of people use natural gas. They boil water, and again water. And here's a pump, guys, a boiler pump. They circulate the hot water into a different coil that's inside the air handling unit. Different coil though, inside the air handling unit. And now if they need heat, what do? They set the control to heat. Now your boiler is up and running. I have hot water. I have my pumps based on the control that I need. I'm circulating the hot water to a coil that goes to the air handling unit. And guess what? The air handling unit, the same blower that blew air in the chilled water coil now blows the same air in the hot coil, and it gets you heat in the building. Very simplified. Any question, guys? So this is just to chill the building. That heating is a complete different, it's part of it, but it's not sure. Any question, guys, how to chill or heat a building, a commercial building? Now you can, now Camille, my friend, if you need, building is huge, guess what? You're going to have multiple boilers, parallel, they call them parallel. You parallel your boilers. The same thing, you have multiple boilers, guys, and you hook them up in parallel, and you get more hot water circulated to the air handling unit. And by the way, this will have a hot coil like this, and also this one here this one, each one of them will have a coil. So not just air handling unit one will have the coil that coming from heat and cool. The same, each air handling unit have two coils. One coil coming from the boiler, one coil coming from a chiller. And based on heat or cool you want, it gets you heat or cool. Really cool system. This is as high as you can get in the heating cooling of any building. There's heat recovery and a bunch of other things that gets to the next level, be efficient. How can you be efficient and so forth. But this is, guys, if you're dealing with a commercial building, high profile, like our building, 4,000 amp switchgear building, 99% of the time you're going to be dealing with cooling towers, chillers, and air handling units, and the in-between pumps. Any question, guys, about this? This is a real project that you're looking at, guys, and this was done for General Mills by the mechanical contractor. I don't know if we say who did it. Yeah, Michelle Cooley Erickson did the project. If you look at the bottom, Michelle Cooley Erickson did the project. Any question, my friends? Electrically, all what we're responsible, guys, for all these, 5 things that I told you that we need to power. If you have, of course, you have a boiler pump here that you need to power, of course. Anything that has that pumps need to be powered to get you the heat. Any question? Any question, guys, about this system? This is really what the bread and the butter of this project is. And I always like this one because it's better than what we have. The second, any question, guys, before I leave this one? Everybody knows that these two, the system at the top goes to the air handling unit to get you the cold, and the system at the bottom is actually to chill the system at the top, believe it or not. So, okay. The second one I want you guys to look at is in the back, mechanical engineers, sometimes they're generous enough to share with us. See the back of that paper that you guys have? All the electrical information about your system. Very interesting. That's where Brad, when the mechanical schedule, you guys remember the mechanical schedule? Where did the info came from? The mechanical schedule right here, from all this stuff that you're looking at the back. So if you guys look at CDWP, the circulating pump, water pump, CD chilled, what is that? Chilled water circulating pump, or something like this. You can look at the electrical equipment here, the electrical information, guys. Can you guys see right in here? Let me see if I can grab my highlighter. And this is just FYI. Here's my horsepower. Can you guys see the horsepower here? Here's 100 horsepower here. And here's my system, 480 3-phase. That's all what I need about this pump. That's all what I need about this pump. The rest is mechanical equipment. Chilled water pump. These are all chilled water pumps, guys, and you can see all the most important 2 things is this information for us. The second thing is VFD. Can you guys see where it says VFD here? Do I need a VFD for this? It says yes or no. If no, it's just a contactor. If yes, then you have to provide a VFD for this. Any question, guys, about this? The mechanical engineers will provide this information. When do we need a VFD, guys? Better control, better speed control for the system. So that's for the pumps. Can you guys see the pumps at the top? If you look at the bottom, the second part is for the chillers. Let's look at the chillers and see what they have about electrical about the chillers. If you look at the chillers, guys, so there are 3 types. Can I bring to your attention, guys? There are 3 types of major loads. There's the pumps, there's the chillers, and there's the cooling tower. These are major type of loads. Okay, if you look at the chillers, guys, the chillers are HVAC equipment. Electrical information about them. Can you guys see the KW here, Mr. Bab? Can you just pull up my system here? Okay. That's you. Okay. Electrical. I have to use it here. I have to make you one, guys. I'm sorry. So if you guys look at the chillers, here's my chillers. Oops, that's cool. And here's my electrical information. And now I have this amount of 890. Anybody can read it for me here? 894 kW. And look at the voltage. Anybody can see the voltage as 4160. That's medium voltage chillers. 4160. They're using a medium voltage chillers, guys. The top ones were 480. Can you guys see this? These were for 480. This is, and do I need a VFD? Look at that. No VFD, no VFD. The only one that needs a VFD is the smaller chiller, 460, and it needs a VFD. The medium voltage, guys, when you have medium voltage, yeah, you need a different control system. I'm going to stop at that there. Any question, guys, about the chiller?
What is the 463-360, what does it mean?
460 is the voltage, 3-phase, and 60 hertz.
Oh, I see, okay.
Yeah. This is 4160, 3-phase, 60 hertz. It's right here, so the voltage, phase, and hertz.
Oh, I see, okay.
It's all right.
Okay.
Right here. Any question, guys? And they give you also the amps. Any question about the chiller? The last thing is cooling tower. Look at the cooling tower information. Cooling towers are pumps. And if you guys look at here's my electrical information about them. Piping, electrical information. Here's the horsepower. Horsepower, low, high. Here's my horsepower. This is my horsepower. That's what you need to pay attention to. And basically a VFD. Do I need a VFD, Brad? Yes. So we're requiring a VFD on all these cooling tower, which is basically blowers. All what they are, big fan, huge fan. If you guys know how to read this one, you can hit the ground running in any commercial project. It really is. Done. That's as ugly as it gets in a commercial project. The heating cooling system. I want to bring to your attention, Ryan, my friend, that cooling towers are motors, and you guys know how to size everything for motors, right? Am I right? That we killed that boy. We know how to size the branch circuits, the disconnect, the overcome protection device, the controller for motors. So these are motors, done. The top ones are, the pumps are also motors. Drea, done. We did motors. So we did all the work for these two. And guess what the chillers are? The AC system, cooling system. Did we do that, guys, for the AC system? Yes. I gave you a calculation. And we remember that locked rotor current and so forth, and we size it by 1.25 times the full load current of the chiller, 1.25 times full load current, and you size the overcome protection device for a chiller, guys. What we said 2.25 or 1.75, depending how we're going to do it, and you go down. So all these chillers are HVAC. The chillers are the condensed. We size them based on Article 4. This is Article 4. This is Article 450, right? This is this is Article 430. This one is going to be. This is Article 430. This is Article 430, and this is Article 440. Can you guys highlight that one? And I guarantee you guys know how to do that. The chillers are Article 440. Everything else, we size them based on Article 430. Motors, they're motors. Any question, guys, about this? So you guys are good in the heating and cooling system. And I'm taking pictures of all this stuff. The last thing I want to do, I want to emphasize one thing, guys. Just tell you a few things about chillers here. And how do we size them from the book that we have. And in particular, we did calculation for them, guys. But I want to use... there you go. Okay, for cooling systems, this is just for cooling, guys. Cooling system, as in chillers. The chillers. This is what I'm writing here is chillers. Article 440. Article 440. I want you guys to pay attention to the following. Minimum, there's something called minimum circuit ambiguity. Minimum circuit ambiguity as this is to use to size conductors. No 1.25. Can you guys write yourself? When you see, Spencer, when you see minimum circuit ambiguity 50 amps on a chiller, minimum circuit ambiguity 50 amps, you take the 50 amps and you go to Article 310.16 under 75-degree column and you size your conductor. No multiplication by 1.25. Did you guys hear me? The manufacturers of the chillers, guys, they give you the amp size of the conductor that they want you to use. They already did the calculation for you. And on the nameplate, they put it as minimum circuit ampacity. So every time you see a minimum circuit ampacity, do I need to multiply by 1.25? No. So that's the first, that's on the nameplate. And please write yourself minimum circuit ampacity on nameplate, on the nameplate of a chiller, on the nameplate of a chiller. The second thing on the nameplate of a chiller, guys, is maximum overcurrent protection. I think they call it maximum overcurrent device. Maximum overcurrent, like this is how they write it. Maximum overcurrent device. MOD, maximum overcurrent device. Maximum overcurrent device. Maximum fuse or maximum overcurrent protection device. The same thing. This is nameplate, on the nameplate, and also use to size fuse or circuit breaker. No multiplication with 1.73 or 2.25. It's already done for you. It's already done for you. So Spencer, my friend, you go to the nameplate. On the nameplate, you will say minimum circuit ampacity 50 amps. Oops, size of cable for 50 amps. Maximum overcurrent protection device is 100 amp fuse. So you go and you grab yourself a fuse, 100 amp fuse. If it says 100 amp circuit breaker, Brad, can I use a fuse? No. If it says 100 amp fuse, it's a fuse. If it says 100 amp circuit breaker, it's a circuit breaker. If it says 100 amp and stops, no fuse, no circuit breaker, it's your choice. So if it says, the key point there is about the maximum overcurrent protection device. If it tell you, if the manufacturer wants you to use a fuse and they write the maximum overcurrent protection device fuse, use a fuse. If they say circuit breaker, use circuit breaker. If it didn't say anything, or if they say circuit breaker or fuse, then you can use circuit breaker or fuse. These are the most important things you're going to find in the nameplate.
Be 100 there.
That's it.
Size for 100 amp wires.
Yep. No. The wire is always minimum circuit ampacity. You size it based on minimum circuit ampacity. So these two guys are the most important things you're going to see in the nameplate of any chiller. On the nameplate of any chiller, these are the most important things you're going to see. Now, when you guys did the example with me about HVAC equipment and you size everything for it, I didn't give you the minimum circuit ampacity. I made you calculate it. That's why you multiplied by 1.25, if you guys remember. I made you calculate it. In reality, you're going to find all this information right on the nameplate or on the sheet. This is not manufacturer sheet. This is just design sheet. You're going to find it on the sheets that comes with the chiller. Okay, so these are the most important things about that. And there's a couple of other that's less important. There's maximum continuous current. And I'm looking, guys, at page 170. Another one that's called maximum continuous current. And this one is called rated maximum continuous current and rated load current. Rated load current, and the third one is branch circuit selection current, branch circuit selection current. These two guys, this is basically the full load current of the equipment. If you guys remember with Chad, what we did, we used one of them and you multiply this by 1.25, but the manufacturers, Spencer, already did that for you and put it as the ampacity, so don't worry about it. So these two are your full load current. Rated load current, branch circuit selected current. The manufacturers do some experiments on their equipment, they run them and they say, here's the amp that this equipment, when it's up and running, is going to consume between the compressor and the fans. Maximum circuit current, guys, this is the max that the equipment can handle before basically it goes nuts. It burns itself. The maximum current that can the equipment handle before it burns itself. Design-wise, not big deal for us, not really big deal. As I said, the big deal for us, for you guys design-wise, are these two values. Please, these two you need to, because that's how we size the conductors, how we size the conductor, and how we size the fuse or the circuit breaker. These two are the most important things on the nameplate. The rest of them, guys, is good. If you don't have these two, Brad, if you don't have these two, here's what you're going to do. If you're going to go back, they have to give you the rated load current or branch circuit current, either one or the other. Then you multiply it by 1.25 to find the minimum circuit ampacity. Then you multiply it by 2.25, guys, to find the overcome protection device based on Article 430. So these becomes like full load current. That's what I gave you when you did all the exercises for AC equipment. I gave you that number. And you guys multiply by 1.25, size your cables. They multiply by 1.15, and you size your disconnects. You multiply by 1.75, and you size your overcome protection device, and so forth. This value here, I don't see a whole lot of direct importance for it design-wise anyway. Any question, guys, about this? In the back of, in the homework, guys, they will giving you, Brooks, my friend, they're giving you the minimum circuit ampacity and the overcome protection device, and they say size the overcome protection device and the conductor. There's a couple of questions about that. Piece of cake. Just write directly from the minimum circuit ampacity 310/16. Done deal. Any question, guys, about how the system works and a few sizes about it?
What MCD stands for the application.
Minimum circuit. Minimum over, this is O, over maximum overcurrent protection device.
Oh, I see.
MOD, maximum overcurrent protection device. Okay. Any question, guys, about this? This is really I went way beyond what the chapter talks about just to show you how the system work together. Of course, Eric, my friend, when I showed you guys all these systems. Let's go back all the way. All these systems, right? We put them most of the time, guys. We put them in a big fat switchboard or switchgear, and we call it mechanical panel. That's what we did in our project. We did almost all the mechanical equipment. We put them in two mechanical panels, except with, I think, the chillers, we fit them direct from the switchgear. That's what we did. Everything else, we put them in two panels. Mechanical equipment panel 1, mechanical equipment panel 2. Just be aware that when you get into a major system, you separate the mechanical equipment from the lighting equipment and from the receptacle equipment. That's very common. So you have a panel or panels for receptacles, a panel or panels for lighting, and a panel or panels for mechanical equipment, and the main switchgear, of course. And if you have a UPS system, of course, you're going to have a data. You're going to have a panel or panels for data equipment. So these are kind of how I like what Phil always say. It's big, like chunk of loads, you guys. You take a building, this chunk of load related to receptacles, we're going to have a panel or panels for it. This chunk of load is for lighting, special type light. So we're going to put in lighting panel. Mechanical panel. UPS and data, it's going to be in a data panels. Like you guys have done the PDUs. Remember that PDUs? The PDUs, what are they? They're just panels specialized for electronic equipment, the servers. Any question, guys? Any question, my friends? There's something, the last thing, guys, in this tiny little chapter that you guys have is they have something called, not every building has it. They call it precipitation unit. Precipitation unit. If you work in a manufacturing environment, and you're welding, and you're all these fumes and all these little particles flying in the air, guys, it makes the air not good for the workers to work. So OSHA will force you, and the government basically will force you to clean the air inside the manufacturing floor. Clean it. You have to clean it. Cleaning it doesn't mean you bring air and circulate it. Clean it, you bring the air, and you have to clean the air before you circulate it. Does that make sense? That's only in very dirty environment. Manufacturing floors is a good example. Welding and cutting and all this stuff, flying objects everywhere. So you need to do circulation. Not only just circulate the air, cool and heat the building, but also you need to clean the air. So the Smarter Than Chad guys created something called precipitation unit. If you guys look at page 176, it's called precipitation unit. Of course, I'm going to spell it. Unit, precipitation unit. So if you look at the precipitation, no, I got it right. That's, wow, first time, huh? Precipitation unit, clean the air. That's it, clean the air. And we're not talking about clean the air, guys, from, you're cleaning the air from toxic fumes and flying particles that could hurt my friend Holly if she's a worker in the manufacturing floor and breathing all these toxic fumes. So what do? Guys? They take the air, they pass it through a unit, and the unit, if you look at page, really nice example in page 178, they have they have a blower, and the blower blows the air through this unit, and the unit has basically ionizer and collector cells. They call them ionizer collector cells. So as the unit guys, as they blow the air in the unit, it charges the particles and the fumes and whatever. It charges the little, especially the little particles. It charges it. It gives it a positive charge, and it pushes it. And another panel, guys, is negatively charged. So what happens if you have a little particle with a positive charge and you're throwing it at a panel, a filter that's negatively charged? It sticks to it, and that's how they collect them. So they charge that little part, they pass them through a filter first that actually charge them positively. If you look at page 178, it's very clear. They have a filter, page 178, called ionizer. They blow the air through this ionizer inside the unit. The ionizer just charges every little particle in the air. It gives it a positive charge, and it moves it towards another collector cells. Can you guys see the collector cells, which is negatively charged? They just have a negative charge in it. That's easy. That's through battery or rectification. So now all these flying particles in the air that could hurt me and breathe it and kill me, or any of those workers, guys, are positively charged and pushed through filters that's negatively charged. And they stick to the filter, and then Brad, they go and they take these filters, clean them with new filter. So so they're not only like the filter in your house, guys. You could use the filter in your house, but these filters are much better because not only you're not depending on the filter is actually charged so that it sticks there. That particle is not going anywhere. So when the particles, guys, stick to the filter and the air goes right through the filter, from this side, it's a clean air. So who cares, Ben, for me as electrical engineer and you guys electrical designers, we need to power this piece of equipment. How do we power it? What's in it? It's a motor. How do we power a motor? 1.25 times the full load current of the equipment, 2.5 times the full load current for the overcompression device, 1.15 for the disconnect. What type of controller they want? Minimum magnetic starter, done. So that's how we interface with this piece of equipment. We don't size it. We don't say what size do you want to circulate the air, cubic feet of this. None of our jobs. The mechanical guys will do that. Our job is to power it and understand what it does. Any question? So I'm going to write next to it just so you know it's a motor as far as we're concerned. And what do you do with a motor? You go to Article 430. And please tell me that you know how to go to Article 430 and size for a motor. Am I right? No? What's 430? Any question, guys, about the precipitation unit? Where is it needed? It's needed in every almost manufacturing place. In the past, they never used to care about this, guys. People will die of lung disease because of these particles flying in the air. Now you have to clean. Okay. That's all I have. I do have to give you guys 2 examples about capacitors. So let's have 5 minutes break and we'll continue. Yes.
my mother-in-law thinks too. She's got all these candles.
Yeah.
And that's Mother Mary.
Did you get that? No. I'm sorry, man. I really. Not, I would never tell you something. Yeah, but yeah. But I hope that, did you call me and try to call me last night? Yeah. I'm sorry, man. I would never, I hope that I would never tell you something. But I hope don't get into it. I don't know what the situation is. When he comes here on Thursday, I'll talk to him about it. Yeah. I'm sorry, I hope I didn't put you on. But here's what I can tell you. You see the statistics? There are jobs. No, I know. There are jobs. It's a bummer, yeah. But I hope don't put me in it. Put me in a very tough situation. I would never like to. I would never tell you something. So maybe you can change your mind or whatever happened before. That when I talk to them, you call me and ask for what this is. So maybe they didn't get a hold of my reference. Did you keep other references? One. Okay. My current employee. Okay. Sorry, bud.
Good.
Finally, huh?
Yeah.
Okay, I'm gonna give you guys two examples about how. Do you guys remember what we did? Was it last week when we did correction? We said there are two ways of correcting car factor. Either you correct at the switch gear itself. That's the cheapest, easiest way of correcting. You take the switch gear, right at the switch gear, and you buy a bank of capacitors, and we know how to do it. And size this capacitor to correct at the switch gear. That's the cheapest, most economical way, easier way of correcting. The better way of correcting is to go down to the level of the offenders. The offenders are motors, and you correct right at the level of the offender. And I can't remember, did I tell you guys every 15 horsepower or more? Is that what I told you? 15 horsepower, if I remember, 15 horsepower or more, you correct. Here's what I have. I have a 350 horsepower. I have 350 horsepower, 483 phase U frame. There are two types of frames, guys. U frame is the old type, and T frame is the new type. What type of what? Type of motors, the way they design the motors. Yes, sir. The U frame, and from now on, you always use the T frame. The T frame is the most. If you want to buy anything right now, my understanding is they're all T frame. Okay, so I'm going to get an example about the U frame first. I have my U frame. Can you guys see my U frame? And my U frame motor 483 phase U frame, and I need to go tab into the feeder, right at the feeder, and correct the power factor right at the offender level. Right at the offender level. How do you do that? At the offenders. I want to bring to your attention, guys, we're going to go to tables. We're going to use tables for this. These tables are, if you guys go, please, can you go to table 11-2? 11-2, page 165 in electrical wiring residential, industrial. It gives you a table. the Smarter Than Chad, the manufacturers came up together and they say they did the calculation, guys, which is very similar to what we did last week, based on the kilowatt. Convert the horsepower to kilowatt and find the multiplier, Brad, from the sheet that I gave you, and based on where your power factor for the motor to where you want to be, and you can find the sizes based on what we did. But because motors guys are standard equipment, they came up with a sheet for us. It's standard equipment for the most part. I want you guys to look at page 165. They give you first U-frame, second based on the RPM, the speed of a motor. They based on these and the voltage, and the correction is always assumed. Can you guys see where the assumption of the correction is? 93 to 97. Anybody can tell me why don't they go to 100%? You don't want to go to 100%. If you go to 100% and correct, you are closer to the leading power factor and high voltage. You don't want to be there. So you always, this is the nicest range that you can be, between 93 to 97. No over voltage because of overcorrection, and no bad power factor because of undercorrection. Can you guys see that? Anything in the 90s is great. If close to 100 is not good. Again, because it could move you to the leading power factor and high voltage, which burns your equipment. Okay, so these tables that you guys are looking at, they're based on correction between 93 to 97, depending on the equipment, but that's good. It's in the 90s, and based on the frame and the speed. Okay, so let's go and find these four things for this capacitor. By the way, the rest of them, these other motors, if I give you 50 motors the same way, you do the same calculation. I'm just showing you how this is a switch gear. This is my switch gear here. And you grab from the switch gear cabinet and you put your disconnect switch here to a capacitor, and off you go. And you can have actually this equipment right in here too. But this motor, you go put it right next to the motor. The motor could be way far away. You put it right next to the motor. That 350 could be air handling unit motor, could be a cooling tower motor, a pump, right? Could be anything. All right, let's go size it. Any question, guys, about the given 483 phase U-frame for 350 Mr. Bab horsepower, and the cab that I need to size here? I need to size number 1 is the cab, number 2 is the conductor, number 3 the overcapacity device, number 4 is the disconnect for this cab. Any question, guys? Can I move? Okay, so let's go ahead and size. So now if you guys look at the sizing, I'm going to take number 1 first. We need to size the cab. Cab size, standard size. I have 350 horsepower at 480 volt, and at U-frame, and also at, what else? What's the RPM? If I don't give you guys the RPM, did I give you the RPM for this baby? If I don't give you, what's the most common RPM? 1800. But I will make it clear, at 1800, the most common one is 1800 RPM. Knowing all this stuff, guys, take this one to table number 12-2, page 165, electrical wiring industrial. I know, DJ, you like my errors here. So this is where we're going to take all this information based on this table. 11 because 11, not 12. Okay, thank you. 11-2. Based on 11-2, yep, page 11-2. The upper one, because it's U-frame, guys, what's the size that I need? Everybody can see the size? What's the size? 60. My size is going to be 60. Anybody can tell me what the unit is? K, yeah, K is the first one. Kilowatt, kVA, or kVAR? Your option is kW, kVAR, or kVA. kVAR, VAR because it's tab. VAR. Very important, the units, guys. That's it. 60 kVAR. Could I have done this with the method that we did last week, guys? Yes. But then, here's what you need to know. You need to know the efficiency of the motor and the power factor of the motor. How would I know? I don't know the efficiency at this moment. That's the reason, guys, why they came up with these tables, because that works for a range of frequencies and a range of power factors. Otherwise, I need the efficiency and the power factor of a motor. I can calculate it the same way I did last week, but I need the efficiency and the power factor. And it takes longer. This is just from one table, bam, 60 kVAR. Any question? Does anybody guys does not know how to use this? That table, straightforward. If I were you guys, what I've done in the past, take this table with you. There's a lot. If you there's a lot of other capacitor table, guys. I don't have these tables in the code book. I have it in DeWalt. In DeWalt, guys, 1-13. If you look at 1-13, they have a capacitor rating for different type of motors. And I hope I looked at them, and the one that we have, they don't completely agree on a few things. They don't completely agree on the few things. But you have that table that we're just using right now. As try it with U-frame. I even tried with T and U-frame, and some of them are slightly different.
You can't use it because it doesn't go.
That's another thing. Yeah, you can't use it, but I tried them with ones that does go, and they're slightly different numbers. This is 1-13. Yeah. But for the test, guys, please, I want to refer you guys, just for the test, please use these tables. Okay, so let's go find number 2. What's number 2? The conductor. So we have the conductor, number 2. Number 2, cap feeder. Cap feeder, guys. If you remember, the first thing you need to find is cap conductor. So what did they say? I have a 60. You take the 60K bar divided by 1.73 times 480 equal. Give me 1 second now, buddy. So when you end up with 72 amps. Did I do the math right? Find the capacitor amps. That's easy. 3-phase load. You find the capacitor. Yes,
What did you do?
nothing. I didn't use that one. I'm just telling you that same table is similar to the table that we're looking at in the book, but the numbers are slightly different. And if anybody want to know why they're slightly different, because remember the range that they said 93 to 97, depending on the power factor and the efficiency. So you're in the ballpark. Number 2. Okay. So that's step number 1, guys. Step number 2 is you need to find so we found size the conductor. So that's step number 1. Find the current. Step number 2 is 1.35. You guys remember that one? 1 times 35 times 72, and that will get you 97 amps. And step number 3 is to take your 97 amps, take it to where? 310.16 table under 75-degree column, and that should get you 3 conductors. 3 conductors, each one of them is number 3, A, W, and a G, and a E, H, H, N, assuming they're indoor for the most part. Why 3 conductors? I don't need neutral. There's no neutral for them. And if anybody is wondering, where did they get that number from? I have the, for the conductor, what was it, 450? Where did they get that one, Chad? Here. Yeah, for the conductor, 460.38. This number here, 460.8. If anybody's wondering where did that number came from. Any question, guys? Straightforward, nothing. It's exactly like the one that we did last week. From the only new step here, guys, is just to use the table. We've done that. Okay, can I move to the second one? Yeah. All right, let's go to the second one. Number three. Number three, guys, is overcurrent protection device. And if you guys remember, we take 1.35 times it by 72 equal, we got that one, 97 amps, go down. So that's step number one. Step number two, you take the 97, take it all the way to 240.6, and this is NEC, and that will get you 90 amps. 90 amps overcurrent protection device. 90 amps overcurrent protection device. And if you are in doubt, where did we get this number from?
468B.
Yeah, this is coming from 460.8 and a B, and also a Chad interpretation. CSK. I thought I put CSK on next to that one. Okay, as long as you guys are writing and you're very engaged, let's do 4. 4 as cab, and everything is for the cab here, guys. Cab, oops, I didn't write the cab. I don't need to write it. You guys know we're sizing for the cab. Do I need to write it? No. Cab, disconnect. Is that where we're going to go? Cab, disconnect. The same thing, 1.35 times it by 72 equal 97 amps. Now, the challenge though, you're going to take this one, 97 amps, take it to D and wall, D-wall, 3-12? 3-12, and that'll get you 100 amp, right? 100 amp disconnect. Now, if you have a circuit breaker, do I need a disconnect? Your circuit breaker will be sized at 90 and it will work as a disconnect. It will be able to be locked in open position. They have them, guys, 3-phase with the locked in open position. That will be act like your disconnect. Where does this number come from? I think it's C, wasn't it? That was from 460.8C, if I remember that one.
Sure.
Any question, guys? Any question? I have one more example about 208 system and T-frame. For 208, this is for 480. By the way, these two tables are for 480. If you have a 240 motor, you're on your own. They're not for 240. They're only for 480. And 208, if you guys read under the motor, under the table, it says if you're using a 208 system, increase the cap size by 33%, right at the bottom of these two tables. If you're using a 208, up the size that these tables are giving you by what? By 33%. That's what we're going to do. We're going to up it by 33%.
So on 4 there, on 4, you can't, or just,
Can I move to the next one, guys? Yeah, thank you. Okay, example number 2. Example number 2. Example number 2, guys, the same thing. I have a system, overcurrent protection device. I have my motor, and you guys get the message here. And I need to come from here, disconnect, fuse, cab. Except this system is 208 volt, of course 3-phase. 208 volt 3-phase. This baby is 200 horsepower, and it's a 208 volt 3-phase T-frame. T-frame. Okay. Anybody has an issue with that? T-frame. This is my switch board. This is my box here. And I need to find the same thing, guys. 1 is the cab. 2 is the conductor. 3 is the overcurrent protection device. And 4 is the disconnect. Except the only difference is the frame is different. The frame is different, and the RPM, it's about 1800 RPM. 1800 RPM. Just if I don't give you an RPM, it's always 1800. But let's just clarify 1800 RPM. And we need to go size that baby based on what we've just done. So the system is 208 3-phase, feeding a 200 horsepower motor. I know for 200 is a good choice. Before I do that, let me see if they go as high as 200 on 430. Before I start hee-hee-hawing around. Yeah, they do. It's the largest that they can get. You can't go higher than 200 at 2.8. It becomes too much current. You just jump into 480. Any question, guys? And if anybody wondering what the heck is Chad is doing here, in reality, guys, how do they tie these wires together? They have 2 lugs. One lug right here you have 2 lugs, one going here and one going here. Because you can't just go cut the wire and tie to it. It's not. So the lug coming out of the what do you call it? Circuit breaker has 2 lugs, and one will go directly into the motor. The other one will go to the disconnect switch. That's one way. Or you can have a J-box here. But you can't just put a cable and tie to it physically. How are you going to do that? You can have a J-box right here, or a pull box, and tap from the conductor. Okay. Let's go to Mr. Bell. Can I go to next one? All right, let's go size for that baby. Okay, so number one as cab size. Okay, taking a 200 horsepower motor at 208 volt at T frame at 1800 RPM. If you guys take this one to table 11-2, and remember it's a T frame, so that will move you down to the bottom one. And also 208, don't worry about the 208. So that will get you what's just directly from the table, 50. That's step number 1. 50 kVA bar. That's the first 50. Next, if you guys look at the bottom, you need to up it. If you look at the bottom of the table, what does it say? Up it by 33%. So because of 208, this is what we're going to do. 208 volt, you have to multiply 1.33 times. That's how we up something by 33%. I hope you guys are cool. The K bar. So we're going to up it to compensate for the lower voltage that we're using based on this table. So 1.33 times 50 equal 67 K bar. We're upping it. We're increasing it by 33%. If you look at the bottom, of that table. It says if the voltage is 208, you increase it 33%. This number is coming from for this voltage, and it's from, where are we here? Table 11-2, bottom. The bottom of the table 11-2. Everybody's okay with that one, guys? bottom of table 11-2, it will tell you have to multiply it by 1.33. Now the question would be, is this a standard or not? Is this a standard size or not? For this particular application, guys, I want you to go to table page 167 just to find a few standards. So I want to go take that 67K var, take it to table number, which table? Table number 11-3, page 167, electrical, wiring, industrial. Just use this one for the smaller than 100, guys. And there's sizes for everything. So for smaller than 100, what's my next standard? For 67, I have all the way, I can go all the way, the first column is the standard sizes. 70, can you guys, I have 65 and then 70. So my options go down to 65, no, go up to 70. So I'll go to 70, go up to 70. So the next standard is 70K var.
Are you able to use that table?
You can.
Because it's,
Yeah, it's giving, yeah, it gives you,
it's 240, 480, and 600.
yeah, but
If
they're,
you're looking for standard sizes.
yeah, I'm just looking for a standard size. I'm not looking for kits. I'm just looking for a standard size. That's all. So 70K var. If it's not a standard, guys, can I put my big arrow here if it's not a standard for this? Now, DJ, on the test, please write yourself a little note that says it's not a standard, go up. Okay. See kind of the tricky little thing that we did? The only tricky thing is multiplying by 1.33, guys. Do you see it, Mr. Bell?
So we're going to 70, right?
Yeah, we're going to the next standard 70. Okay, so we still haven't sized the, this is the size of that equipment basically now is this. Now, from now on, we're going to only be carrying about 70K var. Everything is for 70. I guarantee you, Mr. Bew, that some people, when the test, they're going to take the 67 and find the full load current for the 67. You're done with the 67. You now start with the size for equipment, guys. 67 is a calculated value. Now you're going to size the everything based on an actual industry standard. Can I go to the next page? Am I too fast, Mr. Webb?
No.
I think you're lying, Mr. Webb. Wow, DJ is telling me to move. Okay, number two. Number two, guys, is cab feeder. Cab feeder piece of cake. You need the first thing you need to do is IC. I for the capacitor. This will be what was it? 70K divided by 1.73 times 480.
70K.
480, DJ. What's the voltage?
It's 208.
208, thank you. That's where the mistakes, a lot of mistakes come in. Anybody did the math on that? I don't have the math on that one. So you take the 70, divide by 208, divide by 1.73 equal. You end up with 264. 26. Anybody came up with something different? 264 amp.
I did. I got 194.
That's what I got.
Yeah, 194.
You guys are then right. 70, 123, divide by 208 equal, divide by 1.73 equal. 195. You are absolutely right, gentlemen. 195. 195. Look at that 5. Meet the Lord with a 5 like this. 195 amp. Okay, then the next step, guys, is to take the, I'm not going to write the references now. You guys are good. 1.35 times 195 equal. So times 1.35 equal. That will get you 263. 263 amps. 263 amps. And then, right, give or take, Then you take the 263 amps, Mr. Rabab, to table 310.16 under 75-degree column. And I don't have the size here. What do you guys get? Number 250, I want to say? 300? 300? Okay. So how many conductors though? 3 conductors, number 300 KCM THHN, unless you are asked otherwise.
Is that because there's 3 phases?
Yeah.
There's a capacitor in each phase.
Yeah, a bank of capacitors in each phase. Yeah. Did you what they do is we drew that one. They have one cab, tie them together from one side, and they bring phases A, B, and C. And this could be a bank of capacitors, guys. And this, they put it in a box like this. And of course, you need a ground, right? Everybody knows that there will be a grounding conductor going here, G. We size the grounding conductor based on the overconduction device, but we do not size in G. You guys are good now, right? Equipment grounding conductor is sized based on overconduction device. That's how your caps are going to be sitting. Any question, guys? Muhammad, my friend? Do that again. Sounds like horses running.
That's what it's supposed to
Is that? Mr. Bev?
Yeah.
You good?
Yeah, yeah.
Okay, number 3. Number 3 as, what did we say number 3 as? Number 3 is cab over current protection device. The same calculation, guys, 1.35 times 190. I have short memory now. What is it, 95 or 4? 94, what was that one, Brooks? The total? 264 amp. Now we're going to take the 264 amp, take it to 2440.0 and DC. And if it's not a standard, where are you going to go? Down 250? Did it do it right? 250, 1 second, just 1 second. 250. I'm sizing it wrong. What?
Yeah, this other one you went off of the IC right here before you went 135.
There's the
You
IC.
went off to 72 amps right here when you did this one, and now you're going off of it after you do the 1.35.
That's what you did last
Yeah, you did the same thing.
Okay, let's go back to.
Oh, you're into the 97. Okay, whatever.
You got it? No, you want me to go back to which one?
No, never mind.
Okay, I'll go with it with you individual. Okay, any question, guys? We go down to 250. Straightforward, no? Ben, my friend. Okay, the last one, as you guys expected, is going to be number 4, which will be my cab, this, and connect. And it's going to be, I always like to use 1.35 times 94 equal 264 amp. I'm repeating myself, that's why I'm flying here. Then you take the 264 amp, take it to D, volt, 3-12, 3-12, 400 or 200? 400. 400 amp. 400 amp disconnect.
Is that all you have for today?
Not yet. Still have half an hour.
I know.
Don't.
I'm not trying to rush you.
Start to sound like my mother-in-law. Rush, rush, rush. Nobody can even eat the Easter dinner before you rush her. Oops, this is recorded. Any question, guys? Now, if I gave you guys 36 RPM, would it be different? On the test, I'm going to track you. I'm going to tell you the motor is actually, 36 RPM. So DJ, when you say 36 RPM, you're going to go to a different column. Everybody knows, guys, that if I change the RPM for you, you have to go to a different column. So please pay attention to the voltage, the horsepower, and the RPM, and the frame when you use when you size things for the capacitors. So for lightning protection, guys, I'm not gonna do it better than our speaker. It talks about the atmosphere and cloud to cloud lightning, cloud to earth lightning. You guys will read this one on your own. The only thing I wanna is cloud to cloud and cloud to earth lightning. Okay. The most important thing about lightning protection I want you guys to pay attention is a few things. Let me see. Here's a rod. That's it. Right here. I'm going to write them right in here so you guys can be good with your friend Chad. Okay, let me see if I can. Okay, great. So, and it worked too. When you do your lightning protection for Asa Dunwoody, guys, for the building that you have, please pay attention to the following. You have to put them in your drawing. Number one is lightning. What do they call them? Lightning standard lighting term. They call them air terminals. Number one is you need the air terminal. Air terminals are typically 12 inches. Fine. The first thing you need to have an air terminal. That's all. Air terminals. Just to give you a heads up, guys, how we did the air terminals when you design them. A few rules. 20 feet on center. You guys remember? The rule number one. Every external corner of a building, every external corner of a building, 20 feet on center, right? The parameters of the building, and also 50 feet on center for how am I going to say it, guys? The first one, the 20 on the perimeter, that one middle building. For middle of building. That's it. Done. For middle building. Let me mechanical equipment. The last one is one for each mechanical equipment.
And the ladder.
That's tying. That's just tying to the ladder also. For our project, these are the most important things that guys we hear about. Here's the lightning terminal, the lightning rod. You need them 20 feet on center around the perimeter of the building. You have to target every external corner. At least every external corner have to have one next to it. And in the middle of a building, every 50 feet, we end up having two, guys. And for the mechanical equipment, one at the top. We do have a Revit family. Please go to the industrial project, load the Revit family. Everybody, most of you guys have helped you with it, and you are there. Okay? So here's Revit-wise. What you're going to do, guys, Revit-wise, load the family, drop the family like we did yesterday on the parameters, every 20 feet. That's easy. And then annotate, guys, detailed line, have a dotted line or some type of a line that sticks out, and connect all of them together in a loop. And all these spikes for the mechanical equipment, take a loop also, annotate, and connect it to the main loop. So that's basically what we're going to do for the lightning. Okay, so that's number one. Number two for lightning, guys, you need lightning conductor. Lightning conductor, that's what I like about this chapter, because it actually gives you an actual size. Lightning conductor, it gives you an actual size, guys. If you look at page 207, actual size, that's what we use all the time. It says 59 kcm. So you need minimum 59 kcm cover CU. Let's use 59 kcm, or if you're using aluminum because you're cheap, 98.5 kcm AL or longer. So you make sure when you put your dotted line, guys, you keynote them. How are we going to keynote them? We're going to annotate them. Annotate them with the size. I want you guys to annotate the size is going to be minimum 59 kcm copper. Let's use copper. Okay, use the copper one because Chad is vested in the copper conveys. Okay, done. That's the lightning cable. So we have the terminals. We connect them with cables all around, right? Multiple paths. And we're going to drop down to Mother Earth. Remember, what do we do when we go to Mother Earth? We're going to go ground rods. Ground rods, guys. We said every 100 feet. 100 feet on center. 100 feet on center. So every 100 feet, guys, you drop to a ground rod. That's what you're going to be doing. So for the ground rod, I don't think we have a family for the ground rod, at least if I remember right. We're going to have a little symbol, guys, that shows a ground rod, similar what we have done. It looks something like this. That's my ground rod right next to the building, and you drop a wire, annotate a wire in Revit, and tie to it. So ground rods, the size of the ground rod, you can. The size of the ground rod is we're using as 10 feet by 10 by, what is it, the comment that they have recommendation here, 10 by half, minimum 10 by half inch. 10 feet by half an inch minimum. Okay? And by the way, I'm reading right here the recommendation that they have, guys, and you have the recommendation that we did. So this is basically what you need to do for the building. So your building is going to have, if this is our building, guys, it's going to have a couple of, I'm just going to share something similar to this, right? And it's going to be tied together. Let's use a different color to tie it together. So it's going to be tied together like this. Okay, here, here, here. And you're going to have something like this in the middle here. And it's going to tie together also two paths, this way and this way. And then the ground rods, guys, I'm going to put my ground rods around. So here's my ground rod here, ground rod here, ground rod here, and a ground rod here for the most part. And then you drop from here directly to the ground rod. Can you guys see, are you following what I'm doing here? You drop to the ground rod. Done. That's for the most part what your system is. And please keynote them. So right next to the ground rod, write the ground rod size. Copper, by the way, this is copper. The ground rod is CU, copper. So it's going to be 10 foot. So type, Brooks, you're going to type right next to it, 10 foot by half an inch ground rod copper. That's what you're going to do. Or annotate or whatever. Any question, guys? If I haven't helped you guys set up the view for the roof, please let me know. We're just going to move our view all the way up to the roof and start rubbing, turning everything off or hiding things in place, and start rubbing our rods or lightning air terminals. I trust DJ, I still have 15 minutes. Don't start moving around here and there for 15 minutes before you go eat. You have to deserve your lunch today. Safety rules. I'm not going to read the safety rules for you guys. I think our speaker did a great job about the safety rules and all this good stuff. There's a few safety rules. Keep in mind that you can you have to use them. I wanna inform you guys, or let you know, not inform you, Camille, my friend, there are detailed lightning CAD drawings that we gave you. Please go to lightning file, has detailed CAD drawings. Here's what you're gonna do, Holly, what I hope you guys will do. Import them in a drafting view in Revit as is, and call them detailed lightning E14, E15, E16, and just dump them in the back of your book as lightning details. A lot of them, there's like 4 or 5 of them. That's what we've done in the past. It looks good. So we don't do much with them, but it gives all these details about lightning system. It looks like you know what you're doing.
So you dump them in the back of the book. You mean on Revit?
In Revit, yeah.
On a page?
There will be in different pages. They're big. So there will be E14, E15, E16, and there will be lightning detail 1, lightning detail 2, lightning detail 3. Details. That's what we have done last time. They're all in lightning. I believe they're all in the lightning folder. And you just, what did they say? You just have a viewport, dump them in the viewport, and drop that viewport in the sheet that you already copied or created, and name the sheet, and off you go. So lightning shouldn't take you there, guys, that much. Lightning. Any questions about lightning? So that's what this chapter is talking about. Read it. The most important things are these, basically, 3 things. Really is. The air terminals, the ground rods, and the lightning conductor size that we use. Am I missing anything? And of course, guys, as you know, like our speaker said, lightning, you have to tie everything mechanical there. We're not aware of anything. There's a ladder, I believe, that's sitting there. So you have to tie, just grab, annotate a detailed line and tie it to the ladder. That's as far as we can go in terms of lightning design. All the details drawing Mr. Abab are going to be dumped into view, drafting view, and put in a sheet. The rest of it, how does it work? The atomic structure. I trust, Brad, that you're not going to sleep tonight reading the atomic structure. You guys did it with Ryman, and the layer of the atmosphere, slicing it, and where all the science behind it. Read it on your own. We care about the design part. The last thing I always emphasize, guys, we will have a ground rod for the electrical system too. So what we have done in the past, at least, see these rods right behind the building. What we have done in the past, and I don't have to, is we show another. Which color? Let's use black here. Here's 1, 2, 3. These are ground rods tied together, and then tie them to the ground rod. These 3 guys are for my electrical grounding system. 3 ground rods. We show a symbol like this. These are for the electrical grounding system, electrode grounding system, and you tie them to the ground rod of the lightning. Any question, my friends, about the lightning, air terminals, ground rods, and lightning conductors? That's all what we're talking about, with annotation and all these rules that summarize that chapter. Camille, you guys are good with it? Ben, my friend? Okay. I just want to remind you guys that by Friday, please, you need to print the power. I expect you to print complete power, first and second, and the roof view with the lightning by Friday before you leave. The A students and the B, the C students and the D, we can wait until next week. The below D students, whenever. And Ryan, I have not said a single time that I need your undivided attention. Have you noticed that? Not a single time.
Everyone,
Thank you.